Hello everybody, my name is Andrei and I'm the VP of Engineering at Nillion. Today I'm really excited to tell you about the SDK we are releasing just in time for the Scaling Ethereum hackathon. Nillion is a new internet infrastructure for the private storage, computation, and decentralization of data. It is a decentralized network, but not a blockchain, that utilizes a novel mathematical innovation called Nil Message Compute, or NMC in short, and represents a generational leap in technology from a predecessor technology known as Secure Multi-Party Computation, or MPC. Unlike blockchain, network nodes do not run immutable ledgers designed to store transaction data. And unlike MPC, nodes do not have to communicate with one another when performing computation. The resulting new technology opens up a unique, decentralized set of use cases, and it can also be used to enhance many of the most widely used blockchains. However, please note that Nillion still uses blockchain as payments and coordination layer. Now, let's double-click a bit on the blockchain statement and explore why Nillion is important for the Ethereum ecosystem. As all of you know, blockchains are great at decentralizing trust. However, the prohibitive costs of storing large amounts of data, as well as the transparency they offer as a public ledger technology, prevents them from being applied to a lot of use cases, especially ones where privacy is very important. In light of these limitations, Nillion intends to augment Ethereum, not compete with it, in order to unlock new opportunities by enabling the creation of private DEXs, private rollups, private order books, and cross-chain trading execution. And also private voting for DAOs, and one of my favorites, which is private cross-chain non-custodial key management. At the same time, it can be used for new decentralized use cases such as secure password storage, biometric document signing, and KYC AML, secure logging, and even all the way to privacy-respectful personal AI agents. Scaling Ethereum is the perfect opportunity for us, in fact, to put our technology in the hands of the Ethereum community in order to help them unlock all those privacy-enabled use cases. It also marks a shift in our approach from a traditional working behind closed doors to embracing open source philosophy and building together with you, our wonderful community. This, in fact, is a significant commitment on our part because we want to hear what you have to say and to use that feedback to guide the evolution of our technology. Let's take a quick look at the roadmap and the vision for this project. Real technology breakthroughs are quite rare in our community, which makes it very challenging to plan the future. Still, we want to make sure that we are predictive enough in what we release and when we release, so that other projects will trust us to build real applications for their users. There are two major roadmaps that happen in parallel. The first one is for the Nillion technology, and here the SDK release marks the first important milestone, giving the community access to our developer preview version of our technology and also inviting the community to come build this technology together with us. The SDK comes with a local computation network and abstracted payment solution, so developers can focus exclusively on building applications. Next, after the SDK release, we'll go through a period of continuous improvements to the SDK, after which we are planning to release a public testnet followed by a mainnet soon after. The second roadmap is about our path to going full open source. Although we are releasing the SDK binaries right now, the plan is to slowly start open sourcing the client libraries, followed by the actual network nodes, so that by the end of the year, we can become fully open sourced. Having talked about the SDK and the roadmap, let's take a quick look at what will be available today in the SDK. So the main feature that we are shipping the SDK with is the ability to store and retrieve secrets. This means that users can store and retrieve integers and blobs using the local network that is provided through the SDK. and can also grant permissions to other users and programs to compute on their secrets or to access them. The second most important or equally important feature is blind computation. Basically, users will be able to compute functions on integers using any combination of the following operations, such as addition, subtraction, multiplication and division, if-else statements, reveal operations, and modulo. And we are also shipping an experimental feature that allows you to use arrays, basically zip, unzip, map, and reduce operations on arrays. That being said, let's take a quick look at the Nillion architecture and how the network works. So Nillion technology is based on a new mathematical innovation called Nillion Message Compute, or NMC in short, which allows nodes in a permissionless, decentralized network to compute information in a secure way without really having to send messages to each other during this computation. Unlike blockchain, network nodes are not primarily tasked with storing transaction data on an immutable ledger. Instead, the node's purpose is to perform secure computation in a verifiable, fault-tolerant, and decentralized manner. NMC takes arbitrary data, it transforms, it particularizes, it shreds it basically, it splits it, and then distributes the resulting particles across a network of nodes. The nodes can store and run computation on those particles and then return the result to the desired endpoint for reconstruction. The nodes are actually blind to whatever they're computing, and yet they are able to compute at near client-server speed due to the lack of internode messaging, which is unique to NMC. Using a verifiable secret sharing mechanism on the outputs ensures the correct reconstruction of the results, even in the presence of faults. Now, NMC solves the scalability issues, which is specific to traditional secure multi-party computation, which is that in a secure multi-party computation, nodes must exchange information to compute outputs, which could be really, really slow. To give you an example, when calculating 1 million multiplications, for instance, secure multi-party computation technology would take upwards of 28 hours. With NMC, nodes do not really have to exchange information, messages, when they process data. And instead, they are running computation locally at nearly plain text or client-server speeds, which basically makes NMC about 1 billion times faster than secure multi-party computation in such a scenario. Let's take a look at the practical example now. The NMC network consists of an input interface, what we call dealer nodes and individual users, through which data provided by the user gets transformed with blinding factors that were produced by the NMC nodes, and the data becomes unrecognizable. Once that data is transformed, basically it is masked with the blinding factors produced by the NMC nodes, then it is stored in the Nillion network. No NMC node at this point can recognize who owns the data and what the data that they store actually is. For instance, if a user wanted to store their password, like in this example, the password would be transformed into a random sequence of numbers such that the NMC nodes in the network couldn't really make sense of it. It doesn't mean anything to them. Now, if a user wants to change or use the data stored in the network for a particular purpose, they can instruct the NMC nodes to process the data. Once the nodes have completed the task, they send the output to the resulting nodes. For instance, if a user wanted to use their password to sign a document, nodes would then sign the document with the user's password without knowing for whom and what they're working on. The result nodes then run NMC's reconstruction mechanism to obtain the real output, which is the unmasked output. The signed document using the output from the NMC nodes and the masking factors that initially transform the data. Now, the result nodes have obtained the output without having had any insight into the input initially provided by the dealer nodes in this step. There will be a lot more information on blog posts if you're interested in how everything works on a technical level. So please take a look at those resources. Now, let's get to the fun part. We are offering $5,000 in prizes for building on Nillion. Basically, we're splitting $3,000 to novel use cases of blind computation, maybe one or two winning projects. And like, if you're looking for a few ideas as to what you could build, then you could try to implement a secure voting system for those. You could try to implement blind auctions, secure order books, or even maybe some games. Next, we are giving $2,000 to the best application that is integrating Nillion's tech. And this will be just one project. And here we're looking for developers who are willing to integrate Nillion's secure store retrieve or compute functionality into an app and optimizing it for really great UX. We will also provide qualification requirements shortly. Next, I would like to invite Steph to walk you through a concrete example of blind computation on Nillion with an example which is called the Millionaires Program. Thank you all and have fun. Bye.
Hey devs, I'm Steph Developer Relations Lead at Nillion, and today I'm going to show you how to solve the Millionaires Problem using blind computation on Nillion. The Millionaires Problem is a classic MPC scenario where a group of really rich people want to figure out which one of them is the richest without giving up their actual numbers or net worth. We're going to imagine a very similar scenario where three friends, Alice, Bob, and Charlie, are all at lunch and have just finished. The bill comes and they decide that the friend with the highest salary should pay the bill. Alice makes $10,000, Bob makes $8,000, and Charlie makes $12,000. So we know that Charlie should pay the bill, but Alice suggests that this is the perfect opportunity to use Nillion for blind computation. So all three friends can input their salaries as secret integers to Nillion, and then they can run a blind computation function to figure out which one should pay without ever having to reveal their actual salaries. So that's what we're going to build today. And we'll take a three-step approach to solving this. The first thing we'll do is store the Millionaires program on the network. Then each friend will store their salaries as secrets with bindings and permissions so that Alice has permission to actually use those secret integers in the program that she's written. Last, Alice will run blind computation to compare the three salaries, and she'll reveal the output, and that will decide who has to pay for lunch. So all of this code is actually in an open source repo, and you can find it really easily by going to the Nillion docs, docs.nillion.com. Scroll down to Developer Quick Start, which is in the side panel, and you'll see something called Nillion Python Starter. This is a big repo of code with lots of different examples that you can run and use. We have multi-party examples, single-party compute examples, permissions examples, how to store and retrieve secrets, all of those different things. But clone this repo locally and then run through the README to set everything up. So install your CLI dependencies, set up your environment, and bootstrap your local environment so that you have all of the environment variables accessible that you'll need to run the examples. When you've done all that, go to the Millionaires Problem example folder. This will get us started. And this also notes that you need to have set up already. I'm not going to run through this step because I already have a setup, but I'll go straight into the examples. So let me pull up my code and go to this folder. So as you can see, I'm in the Millionaires Program folder here. And let's go to the README to get started. So as we were just saying, in our version of the Millionaires Problem, the three friends are going to finish lunch and figure out who should pay. So we'll take a three-step approach, and let's get into step one, where Alice creates and stores the program in the network. So I actually have a little Miro visualization of this too. So here's step one. Alice creates and stores the program in the network, and then she also needs to share her user ID and the resulting program ID with Bob and Charlie. So let's get into how Alice creates and stores that program. This is step one, so go to the O1 store secret code. In this function, Alice is taking a program she already created called Millionaires, and the full Millionaires program is actually in the programs folder. So I'm just going to go to programs/millionaires so that we can take a look. This is the NADA program that Alice wrote to perform the blind computation. So there's three different parties. There's Alice, there's Bob, and there's Charlie. And each of these parties is providing a secret integer input, and that is their salary. So Alice is providing Alice salary, Bob is providing Bob's salary, and Charlie is providing Charlie's salary. Those need to be in the network or provided at compute time so that this function can run with those three inputs. So that's the setup for this, and lines 12 through 16 or 17 are where the bulk of the logic for this program is happening. So we're trying to figure out which of the three friends has the largest position or largest salary. So on line 13, we're comparing Alice's salary to Bob's salary, and this is just a little if else. So if Alice's salary is larger than Bob's salary, you enter the second line, which is comparing Alice's salary to Charlie's salary. So if Alice's salary is bigger than Bob's and bigger than Charlie's, we'll return integer 0, which means that party 0 has the largest salary. Otherwise, if hers is bigger than Bob's but smaller than Charlie's, that means Charlie has the biggest salary, so return integer 2. If Bob's salary is bigger than Alice's salary, go down to this line and compare Bob's to Charlie's. If Bob's is larger, we'll return integer 1, meaning Bob has the highest salary. Otherwise, return 2, because Charlie would have the largest salary in that case. And so, largest position is output to the output party, which in this case is Alice. So Alice is the person who is running this blind computation function, and based on this last line for output, Alice is the party that will also be able to read the result of this computation, which is returned here. Okay, so that's our NADA program. Now we need Alice to store this program in the network during step one. So this is just a little bit of setup. We're creating a Python client for Alice. The program name is Millionaires, and Alice has compiled this program to a folder, or to a file rather, and that file is accessible here. It's just the NADA binaries for the compiled program, Millionaires program that we just looked at. So this is how Alice stores the program in the network. She stores the program here, providing the cluster ID, the program name, and the path to that compiled binary code. And we also, remember, need to share Alice's user ID and the program ID with Bob and Charlie so that they can do the next step, which is storing their secrets. So we're just going to print those out. And then when we run step 2, we're passing in Alice's user ID and the program ID so that Bob and Charlie know that for the next step. So let's run step 1 from the command line. This is the wrong terminal. Here we are. So we're in Millionaires Problem example. I'm going to run Python 3 and then step 1. Okay, so you can see a couple things happened. Alice stored the program in the network, the Millionaires program. This is the program ID, and the convention for this is the user ID that stored the program. So this is Alice's user ID /millionaires. And Alice is telling Bob and Charlie her user ID, which is this first half of the string before Millionaires, and the Millionaires program ID, which is this piece. So the next thing we'll do is copy and run step 2. You can see that user ID is that string, and then the program ID is that full string /millionaires. So before that, let's look at the logic for step 2. We just finished step 1. Step 2 is to have Bob and Charlie each store their salaries in the network as secrets. And as Bob and Charlie store these secrets, they're doing two special things. They're adding bindings and they're also adding permissions. So the bindings bind the secret to the Millionaires program ID, and that's saying that the specific program ID is allowed to use the secret. And then the permissions is allowing Alice to be the one to compute using the secret. So let's go to the code for step 2. Again, step 2 is where Bob and Charlie store their salaries in the network. So this is looping through any parties that are in this config parties. I'm just going to show you the config quickly. So the config end parties is just Bob and Charlie's information. So each of them has a user key and a node key. You can see the party names are Bob and Charlie. The secret names that they're using are Bob's salary and Charlie's salary, and the values are 8,000 and 12,000. And these all correspond to what we had in the Millionaires program for Bob's salary, Charlie's salary, and then the names of the parties. So that's why that's important. They all have to match up so that the program knows what to expect. So we're getting the party names and the party IDs, and then each of them is creating the secret that they're storing in the network. So the secret value, again, is coming from that config. So Bob's value was 8,000 and Charlie's was 12,000. And then this is where we're starting to create the secret bindings. So the secret bindings are specific to the program. So we're adding in the program ID so that the bindings are bound to the specific program ID. Then we're adding the party. This specifies who is the input party that will provide the secret to the program. And so for Bob's secret, the input party is Bob, and for Charlie's secret, the input party is Charlie. And we'll print that out just to see it on the command line. Next, we need to create permissions. So this permissions the secret and says who's allowed to use the secret. So maybe who's allowed to view it or update it. In this case, we're setting compute permissions. So we're saying a specific user ID is allowed to use it in a specific program ID, but only if they're computing. So they can't read it or see it. All they can do is compute using it, which is why this is a really cool example of blind computation. Alice is given permissions to compute using these secret salaries, but she'll never be able to see them. And so that's why we're assigning Alice's user ID compute permissions for the Millionaires program. And last but not least, we're doing the actual store secrets operation. This takes in the cluster ID, all of those secret bindings, the stored secrets and permissions. So that secret is stored with all of those things and is bound to a program and is permissioned for Alice. And then we're passing the program ID and each of the store IDs, which is where the secret lives in the network, to Alice so that she can run step 3. But let's go back to the terminal and we'll run step 2. In step 1, we printed out the command to pass into step 2. You could also kind of manually type through this command if you had console logged or something, the user ID and the program ID, but just for ease of use, feel free to copy the command from the previous step. So 2 things happened here. Bob stored his secret and Charlie stored his secret. And you can see the bindings and the compute permissions for each friend, Bob and Charlie. So Bob stored the salary of 8,000 at this specific store ID. Charlie stored the salary of 12,000 at this other store ID. And now we'll pass the store IDs to Alice so that she can compute using these store IDs without seeing the salaries. So Alice will use these in step 3. Let's look at step 3 quickly. Okay, so in step 3, Alice runs the Millionaires program computation using those secret salary store IDs. And she'll also provide her own salary as a secret at computation time. Alice could have stored her salary in the network ahead of time, but since she's running the computation anyway, she'll just provide it at computation time. And then she'll also receive the output of the program, and she'll be able to let the friends know who should pay for lunch. So let's go to step 3 in the code. Okay, so here Alice is initializing her client and getting her party ID. And she's creating the computation bindings, which are slightly different than the secret bindings that were previously created when storing secrets. So computation bindings add all of the different input parties. Remember, there were 3 input parties in the Millionaires program. These were the 3 input parties. They were Alice, Bob, and Charlie. So all 3 of these need to be added as program bindings. So this is the first input party. We're adding Alice, and then let's ignore the compute party just for now. This is how we're adding Bob and Charlie as input parties. We're just looping through each of the additional parties and adding them as input parties here. And the output party is Alice. And that's because if we come back to this program, we've designated that Alice will be the one to receive the output. So those are all of the different bindings, the input parties and the output parties. And then the next thing is that Alice will provide her computation time secret. So she's going to provide her salary directly to the computation rather than having stored it before. So she's just passing in that secret value and providing her computation time secret. Now that we have all of those different things, we can create the actual compute function. So compute takes in cluster ID, compute bindings, which are all those input and output parties, as well as any store IDs, which is where those previous secrets live in the network. So Bob and Charlie have given Alice their store IDs to use. And then the computation time secrets, which are just Alice's secrets. That's Alice's secret salary that she's also passing into the computation. In this situation, there's no public variables, but if you had any for your computation, you would just add them in here. And finally, this is where the magic happens. We compute and print the result. So if you remember from the Millionaires program, we're not printing the name of the person paying for lunch, we're printing the index. So either index 0, which corresponds to Alice, 1 to Bob, or 2 to Charlie. So this is just doing a little bit of mapping to the name. So it's taking all of the input parties and mapping to the name. So this will print out who should pay for lunch. Let's run step 3 and figure out who should pay. Oops. So step 2 printed out this Python command for step 3. Again, it's just giving you all of those inputs from the previous step for ease of use. Copy that and paste it into the command line. You can see Alice is providing her salary as a computation time secret, and this is now running the computation. It was sent to the network. This is the compute ID for this program, and compute is complete. The output result is position 2, and so the richest friend is Charlie, and Charlie should be the one who pays for lunch. All right. We did so many things. We learned how to store and retrieve secrets, add program and secret bindings, add compute permissions, and actually compute. And for kind of next steps, or if you want to do more, I encourage you to go to the Nillion documentation and do some reading. At the very end of the quick start, you see places to keep exploring. You can check out more examples in all of these different permissions, single and multi-party compute folders, and then learn about more of the concepts and the Nillion frameworks. I would love to see what you think of this video and what you think of Nillion. Feel free to post on our forum. Check out our open source code on GitHub. We've got lots of different repos. And I hope to see something that you build in the next hackathon. Thank you so much for watching and have a great day.